I just wanted to talk through the probability sections in Chapter 11. It's the stuff that I think starts at 11.4, but I just want to give an overview of this. There's some specific targeted examples on Blackboard that I want you to, of course, work through that will help understand this. I just want to set you up for success. It's a lot like, I feel like, the financial formula section, in that once you know what to plug into, it's not hard to do. So I just want to talk you through the things you're going to plug into, and then you're going to practice the examples, and that's going to be where you get the real power. So let's talk about probability. And the first type of probability I'm going to talk about is theoretical probability. This is the formal probability that's going to happen when something happens. We have this idea that outcomes are equally likely. To contrast theoretical probability and in another type of probability called empirical probability, I'm going to make an example to contrast two things. It's not quite true for theoretical because the outcomes aren't actually equally likely, but I think it does provide a good feel for what the difference is. So we have things that we call events in probability. Events are things that occur, and we usually denote a random event by E. We'll also use the letters A and B, a lot like set theory. Half the time I'm convinced that I ought to teach this class with this Chapter 11 put right after the set theory chapter. Because I think that there's some very much definite connections. So if set theory stuff was giving you trouble, go back and review some of that before you hit this. But here's the idea. The probability that event E occurs, well, what is event E? E is the thing that I'm interested in talking about. So I write this sort of simplification. You have a similar formula in your book, but I call it this way. Number of desired outcomes. How often do you get what you want? That's the top part of the fraction bar. And on the bottom part of the fraction bar, you put the number of total possible outcomes. And it's when you're talking about this number of total possible outcomes at the bottom that I think you suddenly understand why we talked about counting and permutation and combination. Those are ways to quickly count how many total possible options there were. So these things help give us the denominator of our fraction bar for probability. So here's my sort of, and I promise this is a sort of a bad example because it's not quite true. These are not really equally likely outcomes. But for theoretical probability, we might have this. Let's talk about some natural disasters. There could be tornadoes, there could be hurricanes, there could be earthquakes, or there could be volcanoes. And suppose each of these was equally likely, I might say, well, that means that in Victoria, when it comes to natural disasters for volcanoes, I've got 1, because that's the desired outcome, out of 4. And so there's a 25% chance of volcano. That's not entirely true, but because of course it's volcano I don't think is equally likely in Victoria as, let's say, hurricane, and maybe even tornado is more likely than volcano. If we were in Los Angeles, where I come from, then so much it would all be about the earthquake. On the other hand, we've got, and so this is our theoretical probability. The idea is you know that you have equally likely events, and you figure out what those calculations are. So for theoretical probability, we would so much use permutation, combination, the counting principle, fundamental counting principles and stuff. We use those there. On the other hand, we have empirical. Much like deductive and inductive contrasted our ideas of taking some particular things, some particular examples, and coming to a general conclusion, or taking a general conclusion and applying it to a particular example, theoretical and empirical is kind of the same way. Theoretical has this idea that I know I have equally likely outcomes, and they're all potentially possible. They're equally likely, and I've thought through all the ramifications. Empirical is all about what I've observed. So in empirical stuff, I talk about the probability of my event being the number of observed occurrences divided by the number of total observations. You use empirical a lot if you're doing, let's say, a psychology study. I do a survey of 100 people and I say, how many of you like chocolate ice cream? I've observed that 70 people like chocolate ice cream. I did a total of 100 observations, so I say there's a 70% chance of people liking chocolate ice cream. In Victoria, I would probably, if I was doing observations about natural disasters, I think that I would probably observe that tornadoes and hurricanes were likely. If I looked at the next 3 natural disasters, I suspect that maybe we'd have 1 tornado and 2 hurricanes, so my chance of tornado is 1 out of 3. There was 1 option for this to happen, and the total number of things was 3 things that occurred. So that's what theoretical and empirical is like, and that's what you're sort of looking at. Then in one of the next sections, we talk about the difference between not and or. And again, just like in set theory, we have this word complement suddenly show up. And it means the same thing. Complement, just like in sets, the idea of complement is it's everything that's not my event. So they have this formula. The probability of not E happening is going to be 1 minus the probability that E occurred. So let's talk about something cool. Let's talk about a die. It's the single for the word dice. I don't have a pair of dice. I have 1 single die. And so we know that there's 6 possible outcomes here. If I call my event the chance that I roll a 1, then I know that the probability of that's 1 out of 6. So the probability of the complement of E happening is going to be 1 minus 1/6, which in fractions we call 6 over 6 minus 1 over 6, which is what we call 5 over 6. So there's a 5/6 chance that I do not roll a 1. So that's what complement is. And again, 1 as in 1 is the decimal form of 100%, because you know that 50% we would rewrite as a decimal as 0.5. So 1's the most that can happen because there's a 100% chance of something happening. As soon as I start talking about this idea of complement, well, you have this idea that you've got in a set, you have your universe, and if you have your set A, then your complement's all the stuff that's not A. And as soon as I talk about that, we come back to, again, another idea of set theory about mutually exclusive. And complements are automatically mutually exclusive. There's no doubt that since I have my set A and then I have not A out here, A complement. So of course that all this stuff, this is all the stuff that's not A. So automatically those are mutually exclusive. But there are other things that are mutually exclusive. You can't be a registered Democrat and a registered Republican at the same time. But Republicans and Democrats aren't complements because you've got independents. But still, if you're talking about what's the chance that I have A and B, A or B happening at the same time, remember this is my union symbol, which is what we use for our logical OR. Well, if they're mutually exclusive, all I need to do is add up the chance that A happened plus the chance that B happened. If they're not mutually exclusive, though, just like set theory, they've got that overlap, and just like set theory, we have to subtract off the fact that when I do the A part and then I do the B part, I've double counted this middle. So if they're not mutually exclusive, then I take the A part probability, I add it to the B part probability, and then I subtract one of the double countings in the middle, one of the double places where I've doubled up on there. So again, if you think about this in terms of set theory, you're not going to have any problems with this probability stuff. And then the last couple of words I want to talk about and discuss, I guess 3 of them, so it's not quite a couple. Independent events. Well, if you're independent, that means you're all on your own, you're by yourself. Independent events. Well, independent events, A and B both can occur. So, mutually exclusive events are not independent. Mutually exclusive means you can only have one or the other. For independent events, both A and B get to occur. The idea is they have no influence, no effect on each other. So, for example, there's a certain chance that I'm going to go home tonight and I'm going to have cookies and milk. There is also a chance that President Obama is going to eat pizza for dinner. He's in Europe when I'm talking about this. I think probably by the time you hear this video, he won't be. However, while there is a chance of both those happening, and I could talk about the chance that I eat my cookies and that President Obama eats his pizza, and yet the fact is that whether I eat cookies or not has no influence on his pizza eating, and whether he eats pizza also has no influence on mine. So these are what we would call independent events. They have no effect on each other. I suppose if he and I were friends, I could probably call him and say, hey, Mr. President, I just ate some cookies. Maybe you might think about eating a pizza. And that would have a completely different effect, but I'm not friendly enough with Mr. Obama to do that. So we have this idea of independent events, and they occur together. If they do, and if I have two independent events, let me use my A and B notation again, and I do this A or B going on here, then the way that I see their probability, I don't add it together, I multiply. Both the events can occur, and I'm curious what's the chance that they both do happen. So I've got this, I multiply it together. On the other hand, I could have the idea of things where I don't have independent events. So I could have dependent events. This is where the two events occur, but one does have an effect on the other. An example of this might be the chance of me buying a yacht. Well, the chance of me buying a yacht is going to greatly increase if I've also won the lottery. So the chance that I win the lottery and buy a yacht is going to be just a little bit bigger than the chance of me doing one of those two separately. There's some sort of dependent effect on them. So if I'm talking about dependent events, and I'm trying to chain them up, well, the first event, we usually think of A happening first if we're going to put any sort of time on this. But my second part, it's not just the probability that I buy a yacht, it's the probability that I buy a yacht given A occurred. We don't want to write B given A occurred all the time, so we have this special notation for it. The probability of B such that A. Again, going right back to that such that from roster notation and set theory. And here's how you can figure out what B such that A occurs. It's the intersection, it's the number of times, if I think about empirical things, the number of times that both B and A occur, divided by the number of times that A occurred. So again, I'm not just seeing how likely it is that I buy a yacht, I'm seeing how likely it is that I buy a yacht, and I'm not dividing by the total number of purchases I've made in my life, I'm just dividing by the total number of purchases I've made after I've won a very good yacht lottery. So this is the number of joint outcomes, that and space in set theory, this stuff right here, divided by the number of A outcomes. So again, divided just by this. I'm not dividing by the entire universe. I'm just dividing by the stuff in that A set. And that pretty much wraps it up. There's one last word thing that I do. In English, sometimes we say nasty words like at least or at most. And these are kind of hard to translate into math. So if you ask somebody, what's the chance, the probability of at least one? That's kind of hard to calculate. However, it's usually pretty easy to figure out what the probability of never is. So what's the chance that something never happens? because you can figure out that. And so if you do 1 minus never, that's going to give you that's a complement of at least 1. So you have this complement relationship that you're able to exploit. So when you have nasty English words that are kind of weasel words, like at least or at most, and it's like, well, that means what? Now, if I say at least 1, well, it could be 2 or 3 or 4 or 15 or who knows, 37 even, any sort of crazy number. So when you're dealing with something like at least 1, you can handle that by saying, well, forget about at least 1 or 2 or 3 or whatever it's going to be. Let's talk about what's the chance that this never happens? What's the chance that I never get a parking ticket? Okay, I'll figure out that chance that I'll never get a parking ticket. And then I'll subtract 1 from that, and that will tell me what the chances of that I get at least 1 parking ticket. And yeah, I have just written 1 over 10,000 because I think if I lived 10,000 lives, that maybe one of them probably wouldn't get a parking ticket. But again, I do come from LA, where everyone loves to give you parking tickets. All right. I think that's a pretty decent overview of the language that we use in this probability section. Now, again, tackle the examples, look at those, send me emails, and then it will start to make sense as you actually do some of this. It's not big ideas. You've already looked at the set theory. You've put the work in. It's just you have to practice it with this new language.